and present this joint work with Luca De Dola from the European Central Bank. But what we have in the paper is our own views and does not represent the views of the ECB. Now, as a motivation, let me just say that, as you see on this picture, nominal interest rates in many advanced economies have been constant for years. If you look at the federal funds rate in the US, it's been constant at 25 basis points for something like 7 years now. In the UK, the same situation. In Japan, here the scale is different. So this is 50 basis points, and we know that before that it was 0 for a very long period of time. But also in places like Switzerland. In Switzerland, they actually went to negative 75 basis points for. But we know that there is some lower bound interest rates given by the cost of storing money, so they probably cannot go much lower than that. And in the euro area, since the end of 2014, again, the policy rate is like 5 basis points. So basically, this is a situation when the nominal interest rate controlled by the central bank cannot react or does not react to economic conditions. And there has been a growing recent literature that shows that this situation of constant interest rates leads to the amplification of demand shocks. Okay, there are papers by Woodford, Cristiano Eichenbaum, Rebello, Del Negro, etc., which show that the drop in the natural real interest rate has larger deflationary effects than if policy followed the Taylor rule. The natural real interest rate, you can think of it as the real interest rate in an RBC model. But forget about this. This just to say that demand shocks have large deflationary effects, much larger than if the central bank followed, say, a Taylor rule. And a Taylor rule is one that relates the nominal interest rate to inflation and possibly output. Okay. The government spending multiplier is potentially much larger than 1, okay? And forward guidance is extremely powerful. Forward guidance are announcements about future changes in monetary policy. And in this situation, when the nominal interest rate is held constant now until these future periods, this again has these large amplification effects. And Egerton and Krugman in general talk about topsy-turvy world where everything that we learned in macro is turned the upside down. And so they talk about paradoxes of thrift, toil, and flexibility. I will not talk about the paradoxes of thrift and toil, but talk about the paradox of flexibility, okay, in this. Okay? So what is the mechanism? Suppose that the nominal interest rate is held constant for some period from period 0 until capital T, and afterwards the central bank follows some policy rule. That policy rule can be either Taylor rule or constant money, or you tell me, whatever. Then from the consumption-Euler equation, we have that consumption in deviation from steady state equals this cumulative sum of inflation from period 1 to capital T plus consumption in period T. And now if you take this T to be far enough into the future so that the effects of the shock have died out on real variables, this is approximately 0. And so the effect of consumption today is basically proportional to this difference between the price level upon exit, P cap T, and the price level on impact. Okay? Now suppose there is a shock to government spending. It can be a different shock, it doesn't really matter. But suppose there is a shock to government expenditure. Now, if policy is such that it allows the price level at exit to exceed the price level on impact, then from here you see that this crowds in private consumption expenditure, and the government spending multiplier is going to be larger than 1. Okay, if on the other hand, well, but it all depends on the monetary policy rule upon exit. Okay, so if you have a Taylor rule, then we know that it allows for a drift in the price level and you have this crowding in. But if instead you had constant money, then the price level upon exit is again a steady state price level, so that goes down. The price level on impact goes up because the shock is inflationary. And then we have the opposite. We have crowding out. We have the typical crowding out of government spending. Okay, so what is this paradox of flexibility? The paradox of flexibility is that as you increase price flexibility in these models, there is a larger response of inflation and even larger amplification. Why is this a paradox? Because we know that in the limit with fully flexible prices, the government spending multiplier is less than 1. Okay? But here, what happens is that as you go closer and closer to full price flexibility, the multiplier grows more and more above 1. In fact, grows unboundedly. Okay?
Well, okay, I understand. But that seems to be... So the limit is not...
So there is
and you said the limit. You said the limit of this is the flexible price.
Yes, and
we don't converge there.
No, exactly. There is discontinuity at infinity. Exactly. So that's the paradox. We don't converge monotonely to the.
Don't converge at all.
Yeah. No.
Not
no. Okay, but so what? So. The existing papers all assume a particular type of pricing, which is known as Calvo pricing, which means that there is a constant probability of adjusting prices. And this has been criticized for various reasons, but in context of this paradox in particular, Ohanian has shown that these results, the analytical results about the government spending multiplier exploding, depend on the parameter of rigidity in the Calvo model. And that's an exogenous parameter. So we don't really like, so he says, look, incentives to change prices may change during turbulent times. And so you don't want to hold that constant, okay? And we know that in general, the details of price setting at the micro level may matter a lot for the dynamics of aggregate variables. We know from Golosov and Lucas, for example, that in a model in which the average frequency of adjustment is the same as in the Calvo model, the price level is a lot more flexible, in their case, to a monetary policy shock, okay, to a money growth shock, in fact. And so the reason for that is that basically, it was already discovered by Kaplan and Spuber, is this selection effect. So the firms that adjust prices are not randomly chosen from the population of firms like in the Calvo model, but these are firms for which adjustment is most valuable, okay? Firms for which the gain from adjustment exceeds the menu cost. It's a menu cost model. And these firms are far away from their optimal price. They're in the tails of the distribution, and therefore a shock causes a big change in this distribution because you have a redistribution from one tail, from one tail to the other tail, and that moves the average price level a lot more than in the Calvo model. I'm sorry I don't have a picture of that, but that's basically a known result in Golosov and Lucas. Yes.
So I'm curious there in these models, when you're at that zero lower bound and the multiplier is above 1, is it, from the welfare point of view, is it a good idea to spend for the government? Oh,
so yeah, so Cristiano and co-authors look at that and they find conditions under which it is a good idea. Yeah, even government expenditure that is totally wasted. And
whereas when you're above from it, then that's hard to get, or
then it's welfare detrimental, yeah, okay, to throw away resources. But in this case, it can be. So they like to give this example that, you know, pulling your kid by the hand is not a good way to walk on the street, but it can save his life if he's, you know, about to be run by a car, you know, so something like that. So. Okay, so what we do in this paper, we look at the effect of a government spending shock when the nominal interest rate is held constant for T periods across 3 pricing models: the Calvo model, the fixed menu cost model of Golosov and Lucas, and an encompassing model. And this encompassing model is smoothly state dependent in the sense that the adjustment probability is a smoothly increasing function of the adjustment gain. I'll be specific about this in a second.
So that's going to be a policy change, and people know that after the policy change, you go
to a rule. Yeah. So
you stay in an absorbing state.
So there will be a constant interest rate for, say, 2 years, and then you will be following the Taylor rule. Okay.
Just some lack of knowledge on the literature. So this smoothly state dependent is different from the flexible price because there's there's still some kind of
There's
function?
stickiness, yes. Yeah. It is similar to a stochastic menu cost model. So instead of a fixed menu cost, which is this one, the Golosov and Lucas, it introduces some randomization in the menu cost, which introduces some randomization in the timing of adjustment, which mutes this strong selection effect that is in Golosov and Lucas. In Golosov and Lucas, the timing is perfect. You adjust exactly when you need to adjust. So here you get some randomness, and so you move away from the fixed menu cost and in the direction of Kao, but you are somewhere in the middle. Okay, so in that sense, and I will be in a second talk to you how this is an encompassing model. And we look at different monetary policy rules with or without constant interest rates. And what we find is that with constant interest rates, state-dependent pricing produces even larger amplification than CAV. Okay, so Hania maybe expected that it will resolve the paradox, but we find the paradox even bigger with state-dependent pricing. And so these surprising results at the zero lower bound are really a feature of sticky prices and not just an artifact of Calvo price setting. Okay, Phillips curve becomes steeper. That's not interesting. Okay. Okay, so there's a very large literature on the zero lower bound and on constant interest rates in DSG models. There are papers that do normative analysis, optimal monetary policy with a zero lower bound under commitment and discretion, etc. We don't do any of that. There are empirical studies. We don't do that either. So and we do not pretend to say anything about reality here. So we just shed light on a theoretical mechanism. It's a theoretical mechanism, okay? In particular, we'll be getting multipliers of 50. We don't want to say that this is, really the government spending multiplier is that large, okay?
Okay, but so, then why you do this?
The question was whether state-dependent pricing will solve the paradox. And we are saying that, look, no, you should look for something else. It's not a solution to the paradox. So it's a small question and a small answer to that question. Okay, so I go to the model and the results. The paradox. So the paradox is that with fully flexible prices, there is no particular amplification of shocks in this very plain vanilla RBC model in the end of the day. And the government spending multiplier is always less than 1. It's bad to throw resources in the water. With standard normal utility, nothing fancy, Just I will show the model right now. Now, if you move to sticky prices, that multiplier and a constant nominal interest rate, a zero lower bound, that multiplier suddenly becomes larger than 1, and even much larger than 1. It can go up to 2, 3 under Calvo pricing, okay? Now, you would expect that as in the Calvo model, you move away from stickiness towards flexibility, you will be moving towards the flexible price multiplier of less than 1. And what happens is exactly the opposite. The multiplier grows and grows and grows unboundedly. And that's the paradox, because we like continuity and we like, in the limit to recover the flexible price solution, and we don't.
But the constant thing is still there, right? That is a restriction, right?
The constancy is there, yes, that's a restriction.
So the restriction is not removed. So
The restriction
why
is
should we
not.
expect continuity?
Well,
That's
that's probably true. Yeah. So the restriction is there, and so with fully flexible prices, in fact, as you move towards more flexible prices, this restriction becomes bigger and bigger because you want to move the nominal rate.
It's not a
Yeah.
paradox.
Yeah. Maybe it's not for you, but for the whole literature, it's like a paradox. Yeah.
Well,
Okay.
That's a result, so
Yeah.
it's not that it's wrong.
Yeah.
So it's a paradox in this is that typically in these models, as you make the model more flexible,
Yeah.
everything behaves more like a fully flexible prices.
Yeah.
In this case, you don't.
Because you add a constraint.
of
Yeah,
course,
you add a
but the
constraint. Yeah.
math is right. I mean,
Yeah.
No.
But let me defend better your paper than you did.
Yeah.
To the answer to your question is when this literature was kind of like the intellectual motivation of the big fiscal increases in 2009, 2010. And then part of the critique was now you're going to have typically these models in equilibrium changes in prices are very small, so they defend the color pricing because of that. At the zero bound, changes in prices can be very big. So the critique was, well, then you don't want to use color pricing anymore, and then if you use a more sensible, more endogenous model, things will wash out. And they're saying,
Yeah,
no, it's
thank
more
you.
wash.
Yeah. Yeah, so Haniel made that point in the MBR macro annual in 2010, 11, yeah. And so we wanted to check this in a better microfounded model, you know what happens. And so what we do is we deviate in two ways from the textbook New Keynesian model, which maybe for this crowd here I should tell how we deviate from the RBC model, and that's in three ways. We have monopolistic competition, okay? We have idiosyncratic productivity shocks to firms, that's not in the standard RBC model. And we have price stickiness, which here will be this state-dependent pricing, which nests Calvo at one extreme and the fixed menu cost at the other extreme, okay? And we focus on the dynamics under a constant interest rate, and I will show you how we do that. Okay, so the model on the household is completely standard. We don't do really anything here. You have a standard representative household with utility. The household likes to consume, dislike labor, and likes to hold some real money balances. Consumption is a CES aggregate of differentiated products. There is a standard nominal budget constraint, okay? There's really nothing new. So what you get out of this is the standard first order conditions for, you know, labor supply, for the consumption Euler equation, and the condition for money use, okay? We haven't done anything here. And where the model really deviates is that firms now produce output with idiosyncratic productivity, AIT, which is an AR1 process in logs, and firms faces demands now from two sources, from the private sector and from the government. And the government's consumption is the same CES basket as private consumption. Okay, so the firm faces a standard demand curve. The only difference here is, again, aggregate demand consists of private consumption and government consumption. Okay, the quantity demanded by firm IT depends inversely on the price. You can define period profits as revenues minus cost. W is the economy-wide wage here. And you have the standard discount factor, and we can define the value function here. So this is the value of a firm with idiosyncratic price P, idiosyncratic productivity A, in some aggregate state omega, as current period profit, okay, plus expected continuation value, which is, again, the value of this firm tomorrow with the same price, okay, P, productivity, next period's productivity and next period aggregate state, plus this expected gain from adjustment, which, what is it? It is the probability of adjustment, which now will be an endogenous variable, okay, and depend on the gain from adjustment D, which is just the value difference between the value of the firm when it maximizes its value choosing its price P, and its current value given its current price P. Okay, so this is just a compact way of writing, of encompassing all these models of price setting. And now what we will play with is this gain from adjustment function.
So far
okay.
you're being general with respect to how these probabilities.
Yeah, so far it's completely general. Yeah. So on this slide I'll tell you what I'll do with the probability of adjustment. So in particular, we postulate this function. Okay, you can think of it as, so lambda bar is a constant parameter, and here we have another parameter alpha divided by L, where L is this gain from adjustment that I showed before, raised to psi, and you can think of it. It's a kind of like a weighted average, right, between the menu cost model, which is this, and the Calvo model, which is this. And so in particular, when you take psi go to 0, this becomes constant. It becomes lambda L equals constant. This is the Calvo model. Okay? And when psi goes to infinity, this becomes an indicator function which takes a value of 1 whenever L exceeds alpha, the fixed menu cost, and take a value of 0 otherwise. Okay, and so here is what it means. So here is what it means in terms of the probability of adjustment. So take a big value for psi, take a value of 50. We have this blue line with crosses here, which means the probability of adjustment is 0 up to here, and then it jumps, very quickly jumps to 1. Okay? In the extreme case with psi infinity, it jumps directly from 0 to 1. And with the small psi, okay, that jump is here at 0, and so it jumps from 0 to whatever is the constant probability of adjustment in the Calvo model. But we are interested in intermediate cases where this can be smoothly increasing in adjustment gain, but for different values of the psi parameter. And how do we discipline this parameter? We do it here. Okay, so we look at the size distribution of price changes, in this particular case from AC Nielsen data, and this is this blue shaded area. Okay, and what it shows us is that we have coexistence of price changes which are relatively small and price changes which are relatively large. So it's a more or less smooth histogram, except for this dip here in the middle. And what we know already from the paper by Midrigan is that the fixed menu cost model of Golosov and Lucas has a very hard time matching this histogram because it generates price changes occurring whenever you cross the inaction band. Okay, and so price changes are concentrated in these two spikes, which means that you get nothing in the middle and nothing in the tails of the distribution. Okay, so you get only price changes of a similar size. Now, if you look at the Calvo model actually does a better job, but what it does is really overpredicts tiny price changes. It has the highest probability of price changes that are less than 1%. Okay, so this is this bar here. And what we do is we basically estimate this parameter to fit this histogram as well as we can, and then we generate the price changes of different sizes, and we match this dip in the middle, and our estimate is 0.23. Okay. Now, okay. Yes.
So one point is that I think, if I understood well, you don't exactly fit the fixed menu cost because alpha is not part of the resource constant, is it?
Is alpha is not part of
in a fixed menu cost there is a resource cost.
Oh, yeah. You can. We actually, when we compute it, we take it out. Yeah, it's irrelevant for the impulse responses.
So it doesn't matter.
It doesn't matter quantitatively for the impulse response. So the resource cost is 0.2% of the average firm revenue. Okay.
0.2, not 2. Okay.
No, 0.2. Yeah.
So these price changes, was that for a long time series or just one cross section, or?
So this is AC Nielsen, but it's similar if you look at other histograms like Dominic's data, for example. The ones that are publicly available at least have this feature that they have this relatively bell-shaped with a dip in the middle. Yeah.
Okay, but that's all in normal times and in. So do we have data on that? What it really looks like at the zero lower bound
with the crisis. I haven't, this data is usually not publicly available, so you have to work for the BLS or be a consultant or something. And we haven't seen data. We're trying to get data at the ECB from AC Nielsen for this recent period, but we haven't yet gotten any. So I haven't. So this is data before the crisis. Yeah. Okay, how am I doing on time?
20 minutes.
Okay. All right, so the monetary authority follows the Taylor rule, which is this. So it says that the nominal interest rate has some constant intercept, and then it reacts to inflation with some coefficient that has to be usually larger than 1. Okay, and this series of shocks which are chosen so as to kill this endogenous dependence on, so basically to maintain the nominal interest rate constant from period 1 to capital T. Okay, and the important thing is these shocks are anticipated in advance. Okay, and the government spending is just an exogenous Air1 process. So this epsilon is, if you look at the timing here, these were determined in period 0, okay, but they will be effective in period from 1 to capital T.
Isn't it simpler to say it's going to be constant until capital T?
I can say like this, yeah. I can say like this, yeah. This is just the way we implement it, but in principle it's going to be constant, and then there is a Taylor rule. That's the code, yeah, the code is like that. Okay, then doesn't matter.
So what is it? No, it matters because I didn't understand it. So.
Oh, so these are a bunch of state variables that are set in advance, so that we have to solve for, so that this thing is constant, so that this thing exactly offsets this, the endogenous part.
For cap T periods.
Yeah, for cap T periods. Yeah.
So cap T plus 1, what happens?
Oh, cap T plus 1, these are no longer there, and what follows is this. So these are only valid from 1 to cap T, and then the nominal interest rate starts to move with inflation.
But these epsilons
This is
are...
not at all what you wrote. So anyway. So
What do you mean?
What happens is IT equals I star from T to 1
Yes.
to cap T,
And then
for T
this.
bigger than cap T, then there's the other. Okay.
We have the Taylor rule. Yeah.
Is that what it
Yeah.
is? Or-
Yeah.
But
What else do you think it could be? I mean, that's what it is. Now, I mean,
No, but I mean, if I read this, what I would
Yeah.
understand is these epsilons are very complicated objects, no? Because you have to balance this phi.
yeah. So you have to invert the matrix
kind
to,
of a
yeah.
fixed point.
No, well, is it a
Because you need
fixed
to
point?
accept
You have to
that it
invert.
reacts to endogenous variables.
Sure. Yes. So you start from the. If I remember how we did it, you start. But you can do it. I mean, there's no.
No, you can't do it,
Yeah,
I
there is
understand.
no.
But that's different than assuming that I
No conceptual.
just erasing the rest. It's not. Okay.
I mean, it's not particular.
Is it
It's
different?
3 lines of code to do this. What is different? What is different?
What he said from what I said.
I'm not sure I understand you guys. Sorry.
Yeah.
What do you think is different?
Well, I mean, one thing is you assume that this is rule for a while.
No.
And then afterwards your rule changes. Other
Yeah.
is rule is always this, but you do something to keep it these two cancel. These are different things, in my opinion. I don't know.
So what matters?
That's fine. That's I agree.
Okay. Okay, I think it's the same.
Okay.
Yeah. No, the important thing is there is a subtle point here because this has to satisfy some restrictions so that you ensure unique equilibrium. Because if you had only this forever, then equilibrium is not unique in these models. Okay. But the important thing is that this Taylor rule kicks in at some point to stabilize inflation.
So what if you had a real balance in the utility? So it seems like it's not going to play any role.
No. You can think of it as a cashless economy. The only reason we have it is we're going to have also a money growth rule. And so we'll look at how that works. I mean, this is really plain vanilla New Keynesian model. So Okay.
Vanilla is less plain than you think.
Okay. All right, calibration. Okay, we lift many parameters directly from goals of Lucas. So the time discount factor, the coefficient relative risk aversion, the elasticity of substitution between goods, labor supply elasticity is some standard value from the literature. Inflation target is 0, is as in our data set. So in our data set, there is the mean price change is 0, so the inflation is 0. The inflation reaction coefficient, so this has to be above 1 for uniqueness of equilibrium. So we just pick 2, which is a common value in the literature. Length of the period, this is monthly, so either 2 years or 3 years, as in Herzog and Linde, of the constant interest rate. Persistence of the shock, again from their paper, 0.9. Persistence of the, these were taken from our previous paper where we matched this distribution. Thank you. Thank you. So basically, we have these 3 values for the 3 models, 3 values of Xi, 0 which is the Calvo model, 1 which is the Golitsov and Lucas, and 0.23 which is the encompassing model. The fixed menu cost is that much. That corresponds to 0.2% of revenues of the firm. In the Calvo frequency, in the case of the Calvo model, is 10% per month, which is again also standard in this literature. So 10% of the firms adjust their prices per month. Yes.
So is it a problem that so your economy, the zero lower bound is hit at a certain calendar time, right? So it could have been 2001, right? Or whereas in reality, right, you're hitting it probably in some situations that are specific. Do you think that matters, or?
So we will not be actually simulating exactly this. We are simulating a constant interest rate. So for everything I say here, it's irrelevant whether the constant you have is 0 or it's a steady state. Okay, it's any number. Give me your preferred number for, you fix the interest rate there. The important thing is you don't respond to endogenous variables. So that's what gives the amplification of shocks. Okay, but the level of the interest rate is irrelevant. Okay. Okay, so let's go back to your world. Here is you have flexible prices, and it's very easy to show that the multiplier is always less than 1. Actually, the limit given this utility function, actually it can be at most 1 with linear labor disutility, which is a really special case when this is 0. Okay, but as we'll see, these things change once you have the zero lower bound and sticky prices. So let's go to the sticky price model. Actually, I don't need, this will just complicate things for you, and it's not, you don't need to see this to understand. You don't need to see, this is just how you log linearize the consumption Euler equation, and that's the Phillips curve. And that's this parameter kappa, which is exogenous in the Calvo model, okay, because it's directly related to the fraction of adjusters, etc. Okay, now suppose there is so this is okay, this is with the Taylor rule. So now let's go to the Taylor rule, but still no zero lower bound, no constant interest rates. Again, you can and suppose there is some shock with a given probability, with a given persistence rho, and you can solve for the multiplier in this case in the Taylor rule, and you can again show that it's always less than 1. Okay, so if you just throw in sticky prices, nothing changes much. You're still getting close to the flexible price result. Okay, and moreover, here in this world, there is no paradox. As you increase kappa, so that means more price flexibility, that leads to a smaller multiplier. Okay, so you move closer and closer to the flexible price limit where the multiplier is really small, or small, it's less than 1. Okay, so this is what I show here. Is that what I show here? Taylor rule, yes, Taylor rule, the multiplier is similar. Okay, so here we have this shock to government spending, 0.1% of GDP. All right, this shock is inflationary, so here we have three types of models. We have the Calvo model in the red line with dots. We have the fixed menu cost model of Gosov and Lucas, which is the green line with squares, with circles. And we have this intermediate model, which is the smoothly state-dependent pricing model, which is this blue line. So, so prices jump on impact in all three models and by a similar amount. And then, of course, the more flexible models generate, under a Taylor rule, okay, generate a bigger drift in the price level. So the prices rise more in the Gosov and Lucas model than they do in the Calvo model. But what that means is that because here the central bank reacts with the Taylor rule to inflation, you know, the nominal interest rate rises by more than inflation because of this coefficient of phi equal 2, which means that the real interest rate rises by more with state-dependent pricing, which means the consumption is crowded out more, actually, with the more flexible model, with the Gosov and Lucas model. And so if you look at the fiscal multiplier on impact, you see that it's around 0.8 in the Calvo model, and it goes down slightly. With the more flexible models give you a multiplier of 0.7 or something like this, but still they're very similar. There is not much of a difference. Okay, but in all cases it's less than 1, and similar to the flexible price case. Now let's look at a different rule. Instead of Taylor rule, let's suppose that the central bank keeps money constant. Okay, keeps money constant. Given the utility function that we have, a constant money also implies constant nominal interest rate. That's very easy to do by substituting the money demand into the Euler equation. You get an expression only for the nominal interest rate and the change in money, and so that implies a constant nominal interest rate. So in this case, no, the real rate is here. It changes. The real rate changes.
Oh, is it? Okay.
The real rate is actually the inverse of inflation. Yeah. So the price level here, the difference here is that, as I showed you in the very first slide, here the price level is anchored at infinity, okay? So you return to the original price level because of the money rule, but it jumps on impact, and so it jumps most in the more flexible, in the state-dependent pricing model, okay? So you have more inflation initially, okay? And that means that here the impact of the real interest rate is bigger, okay? So the drop in the real interest rate is bigger under state-dependent pricing. And again, that means you crowd out consumption more. You have a very similar picture to before. You have a multiplier less than 1, okay? Nothing strange, nothing weird. And you have the more flexibility, the closer you are to the flexible price limit. So nothing strange here, no paradox. Okay, now let's go to the case with a constant interest rate, okay? And here this is Woodford's solution for this case. He obtains an expression in the Calvo model, a closed form expression of the multiplier, which is this, which now you see that as you increase kappa, okay, two things happen. First of all, the denominator increases, but also the denominator, which is this thing here, decreases towards 0, and so this mu, this multiplier at the 0 lower bound, rises without bound. It rises, potentially to infinity. And so Hanian said that, look, this is really limited to the case where this denominator is positive, otherwise this mu is not well defined because of multiple equilibria. It turns out that Werning also showed that this is also valid for the case when the nominal interest rate is held constant for capital T periods, which is our experiment, and thereafter the central bank follows its policy rule, say the Taylor rule. And here the expression is a little bit more complicated from Werning, but basically what you see here is that as kappa grows, okay, you again have an explosion and the multiplier grows. As before, you have the paradox of flexibility. And in fact, the longer is the period for which you hold the nominal interest rate constant, the longer is t, the bigger is the explosion and the bigger is the multiplier. Okay, so what we find for the case of constant interest rate and state-dependent pricing is that what happens here now is that okay, the price level jumps on impact a lot more than with Calvo. Okay, thank you. But it also rises more. Okay, and so what this translates into, so this difference between the price level on exit and the price level on impact translates into this big difference in the real interest rate. So in the state-dependent pricing model, the real interest rate drops by a lot more than in the Calvo model, okay, given that the nominal interest rate is constant, so for 2 years, for 24 months, and then you see how it follows the rule, then it jumps to the rule. And so this crowds in consumption.
Why do they go to different levels after
Here?
The price level?
Oh, because it's a Taylor rule. It doesn't pin down the price level, it pins down inflation. So the drift is different.
But for the first T periods, you keep the nominal interest rate
Constant, yeah. And
So
then you
why do you get such a higher inflation rate with the SSDP?
well, because of this selection effect that Gossov and Lucas found, that you have the
But the selection should work only at the beginning. At the end, when everybody can change prices with Calvo.
well, but you see the big advances are made in the first few periods. The big changes are here in the first few periods. So that's when selection works.
Well, let's talk about it after the Q&A.
Okay. Yeah, selection dies out, but when it dies out, you stabilize the price level
At a different
levels
level.
off
That's what I was expecting. It would arrive
at the
later
same
than
level.
that.
No,
At the
same level. No, with the money rule, yes, but not with the Taylor rule. The Taylor rule,
The Taylor rule kicks in afterwards.
sure.
Okay, we'll talk later.
Okay. All right, so what we get is the multiplier. With Calvo, it goes slightly below 2 with the constant rate. With state-dependent pricing, it goes all the way to 8. Okay. And in fact, we obtain the largest amplification in the Gossov-Lucas fixed menu cost case, where the multiplier goes all the way to 50 or something. Okay, so let me conclude. Oh, we just check what happens if you change the period over which the nominal interest rate is held constant. So here we extend it to 3 years, 36 months. And the multiplier under our benchmark model goes up. Basically, the longer is the T period, the bigger is the multiplier. Okay, so let me conclude with active monetary policy. Under state-dependent pricing, the fiscal multiplier is close to flexible prices, similar to the Calvo model. It's less than 1. But with a constant interest rate, there is a much larger amplification of demand shocks. Okay, and the multiplier can potentially be much larger than 1. And the largest amplification is in the Gossov and Lucas model.
So the fact that you know T for sure does not matter, right? If there's a probability of changing T.
The fact that I know T, well, yes and no. We wanted to keep something constant across the 3 models, so we thought that the normal thing would be to have the same T, yeah, but there is, if you really want to model the zero lower bound, then what you do is you have some other shock that takes you to the zero lower bound, okay, and then T becomes endogenous depending on the persistence of that shock. And the T for the different models will be different. In particular, in state-dependent pricing, you would expect the T to be shorter. So because inflation is more flexible, the price level is more flexible. But then what it means is, yeah, the multiplier will be smaller, but it's because it has done its job. You know, you have used government spending exactly when consumption was below, you know, you had a drop in consumption and a drop in inflation, and the government spending helped you boost consumption and boost inflation. And then you get out of the zero lower bound, and so therefore you're back to a situation where the multiplier is less than 1. And so you get the average of this, it gets smaller. Yeah. But again, you say, oh, it's a great idea to use government spending in this particular situation because it takes you out of the zero lower bound. Yeah.
So, just going back to your slide, guess you didn't want to say anything like reality, but at the end you cannot avoid it. So, so what do you think? You calibrated the prices as best you can do,
Sure.
and you get this 40,
Yeah.
which is obviously not that plausible as a
So-
multiplier.
so-
What is wrong with the model?
So there are two things. First of all, this is a local multiplier. This is really an epsilon shock, okay, that I'm talking about. So I'm talking about $1 and $40. Maybe if you go to not $1 but 1 million, there's some nonlinearity will kick in, and it's not you're not gonna get a multiplier of 40. So that's one possible answer. Another thing is that, well, it can tell you that maybe pricing is not as state dependent. If you don't believe these big multipliers, in particular, notice that this big multiplier is always related to the huge inflation response. Do you believe?
SSDP was really
Yeah.
nice calibrated.
Yeah,
But that
yeah.
comes together with that.
But it comes together with an inflation that is on impact 25%, 25% of inflation. So it's a huge inflation.
Okay, that's what I don't get at all.
Why not?
But
We have other time, so-
okay,
Yeah.
Okay, we can talk about it later. Yeah.
I mean, unless you have a quick answer for this price levels.
For this price,
I don't know if you have a quick answer. I don't know.
no, it's
You
this.
learn anyway.
It's this. It's back. It's coming from backward explosion. That thing here, because you know that it will kick in the future. So it requires you to start. It requires you here already to be raising the interest rate. You're not doing this here, so that means that it's higher. You're not doing this the period before, so it's even higher. So it's all this long period when you should be stabilizing inflation. You're not stabilizing inflation, so therefore it explodes. I don't know if that you understand, or we can talk later. All right.
Perfect.